Welcome to this session of solar design training. In this session, we will explore the foundational concepts of current and voltage, two of the most important parameters in electricity. Understanding these concepts is essential for anyone looking to design and optimize solar power systems, as these elements govern how electrical circuits function and how energy flows through a system. So we'll start with the basics of current and voltage. Electricity is a fundamental aspect of modern life, and at its core are two key concepts: current and voltage. Current refers to the movement of electric charge, while voltage represents the potential difference that drives this movement. Both are essential in understanding how electrical circuits work, whether in small devices or large solar system. To understand the current, we can say current is the flow of electrons through a conductor. It is measured in ampere. Electrons, the negatively charged particles in an atom, move through a conductor when there is a potential difference, the voltage, the potential difference, which is the voltage. So they move through a conductor. The electrons move through a conductor when there is a potential difference or voltage applied across the conductor. This movement of electrons generates current. In essence, current can be thought of as the flow of electricity through a wire or circuit. Electrons are very tiny particles located in the valence shells of atoms, and when these electrons begin to move, they create electrical current. However, electrons need a force to push them into the motion. This force is known as the electromotive force, or simply the voltage. So when we apply a voltage to a conductor, it creates the necessary pressure to move electrons from the negative terminal to the positive terminal. Now we will talk about voltage. We have already talked about voltage, but let's take a look at that as well. Voltage, which is measured in volts, V, is the electrical potential difference between 2 points in a circuit. It is the force that pushes electrons through a conductor. Voltage is what causes current to flow. In other words, without voltage, there would be no flow of current and thus no current. Um, I'm sorry, without voltage, there would be no flow of electrons and thus no current. This is why voltage is often referred to as the driving force behind electrical circuits. In the context of solar power systems, voltage is critical for transferring energy from the solar panels to the battery or the grid. A higher voltage results in a stronger force pushing the electrons through the system, which can increase the efficiency of power transfer. Understanding how to manage voltage in solar system is key to maximizing energy output. We will come to the types of current and types of voltage as well. So there are two main types of current: the direct current and the alternating current. Direct current, the short abbreviation for direct current is DC, and um, for alternating current, it is AC. In DC, the flow of electron is unidirectional, meaning the current flows in one constant direction, from the negative terminal to the positive terminal. This type of current is typically found in batteries and solar panels. And this is how it looks like. So the direct current, you can see it flows from the negative to the positive. In the second diagram, which I'm showing here with the battery, you can see this. This is actually this is actually showing the direction of current. So the direction of current is opposite to the direction of electrons. So it moves from negative to positive. I mean, the electrons move from negative to positive, and the current flows from positive to negative. AC, on the other hand, involves the flow of electrons periodically reversing directions. as you can see in these two diagrams. The oscillation of current in AC creates a back and forth motion of electrons, which is represented by a sinusoidal waveform. AC is the standard for power distribution in homes and businesses, largely because it is easier to transmit over long distances. Solar power systems must often convert DC generated by solar panels into AC for use in homes and the grid. I'll go back to this image again. So, types of current, DC, just to recap, types of current, DC, direct current, and AC, alternating current. The voltage that works on this direct current, or the voltage that produces the direct current, is called as the direct current or DC voltage, and the voltage for AC is AC voltage. So I'm habitual of saying AC current while it is actually alternating current. So if I'm saying in the video, if I will say AC current, I meant AC only, not AC current. So it's AC current is alternating current, which is wrong. And then there are two different these are not types of voltage, but these are two different voltages that comes with a system. When you design a system, you will see these two systems, these two voltages. One is the nominal voltage, which is the baseline voltage, which is used as a reference everywhere. And the second is the operating voltage, which is in use. So you will see many a times the voltage of the system is 480 volts, while the voltage of the system is 480 volts, which is the operating voltage, um, which we are using in the system, in designing the system. And it has a different nominal voltage. So for 480 volt operating, the nominal voltage would be, let's say, something like 410 or 450, something like this. Next up, we have induction of current. How the current is induced, or how the current actually starts flowing or actually originates. And we are talking about the alternating current only. So the induction of current refers to the process of generating an electric current in a conductor by changing the magnetic field around it. This phenomena is based on Faraday's law of electromagnetic induction, which states that a changing magnetic field within a closed loop induced an electromotive force in the conductor. This induced EMF causes a current to flow if the circuit is closed. So in this diagram, in the first diagram for single phase and the second diagram for three phase, we can see that the magnet, actually, let's take a look at the first diagram only for single phase for a short period of time. So when the magnet is going inside the coil, when it is making a movement inside the coil, the pointer inside the meter is pointing to the positive, and when the magnet is going out in the opposite direction of the coil, and it stays there for some moment, the pointer goes to the negative and then comes back to zero. So whenever the magnet is having or doing some movement, then only the pointer is moving to either negative or positive. When there is no movement, the pointer is coming back to zero. So this is how the current is flowing. With the positive, when the pointer is going to the positive, you can think of this as the positive cycle of alternating current. And when the pointer is going to the negative, you can assume that, or you can think of that as the negative cycle of the alternating current. So positive and then negative, positive and then negative. This is a sinusoidal wave that it creates with its motion. The same thing is happening with three phase. So in single phase, we only have one magnet, but in three phase, we also have one magnet. This is a motor. This is an example of a motor where the stationary There are three stationary magnets which are called this part of a stator, which are the part of a stator, and this rotatory magnet in between is the rotor, or part of rotor, I would say. So when the red part of this magnet is coming in contact, or this red part of the magnet is aligned with one of the magnets, you can see that at that time the current is at the positive side or positive high of this waveform. So now it is coming to this blue line. So at the same time, you can see the blue line is, yeah, that was the positive side, or that was the first high of uh, this blue line. That's how, and this when it is not in contact, when neither faces or neither side of this magnet is not in contact uh, of any of the stator magnet, at that time it is zero. Their waveform is zero, actually. Now this in the alternating current systems, the frequency plays an important part. And what frequency is the frequency refers to how many times the current changes direction per second. It is measured in hertz, Hz. For example, a frequency of 50 hertz means the current reverses direction 50 times per second. In most part of the world, AC power operates at either 50 hertz or 60 hertz. Frequency plays a key role in determining how effectively power is delivered in an AC system. Higher frequencies means more cycles per second, which can affect the efficiency of energy transmission, especially in three-phase systems where each pulse is offset by 120 degrees to ensure continuous power delivery. You ask about the frequency of DC, it is 0 hertz. Now, we can take a look at the symbols of AC and DC. And um, here you can see the AC has the same symbol as its waveform. First going to the positive and then it is going to the negative, a negative high and then coming back to zero, or it's completing a full cycle of 360. For DC, it is flat because it is only in one phase. It can either be positive, it can either be negative, but only in one phase. It cannot change the phases. Next up, there are some questions that I would like to answer based on what we have learned so far, which is the connection at home. What kind of a connection do you have at your home? A series connection or a parallel connection? So in series connections, the current remains the same and the voltage changes, or the voltage adds up. In parallel connection, the voltage remains the same and the current adds up, or it changes. So in our case, we receive constant voltage and our current increases with the appliances, with addition of each appliance. Therefore, I would say at our home, we have the parallel connection. Second question, what do you receive at home? And receiving means what kind of a current, what kind of current do you receive at your home? So the answer to this is we receive alternating current. Third question, how many times does the bulb glow? Um, the bulb glow means how many times it flickers actually. So if you're receiving a frequency, if you're in a country where you are receiving a frequency of 50 hertz, then the bulb is flickering 50 times in a second. If you're in US, where the frequency is 60 hertz, then the bulb there is flickering 60 times in a second. All right. The next topic that we are going to talk about is the Ohm's law. So the Ohm's law is one of the fundamental principles of electricity. It states that the voltage V across a conductor is directly proportional to the current I flowing through it, with the resistance R acting as a proportionality constant. So at the bottom right, kept I've kept a note in blue where V is directly proportional to I or V equals IR, where resistance, R is resistance and it is a proportionality constant. So I here is electric current, obviously. V is voltage and R is resistance. And there are different representations or different kinds of different kinds of representation that we can give with this formula, which is V equals IR is one, I equals V upon R is second, and R equals V upon I is third. So yeah, in all of these equations, resistance represents the opposition to the flow of electrons. Okay, let's come to the resistor or resistance because we're talking about resistance now. So as I said, resistance represents the opposition of the flow of electrons. In other words, it is the hindrance in the flow of electrons. Resistance, which is measured in ohms, can be thought of as the friction that slows down the movement of electrons. Materials with higher resistance require more voltage to push the same amount of current through them. This concept is critical when designing electrical circuits, including solar power systems, where resistance needs to be minimized to ensure efficient energy flow. An equipment or an object or something which creates this hindrance or friction in the flow of electrons is called the resistor. So you can see in this diagram, we have a copper wire without the resistor, and we have a copper wire with a resistor, and you can see the difference in between them. Without the resistor, all the electrons are going very, their motion is very good. With the resistor, their motion is just their zigzag motion, they're juggling in between them. Okay, so the next topic, oops. The next topic is power. Single phase power and three phase power. The single phase power systems are common in residential buildings and small commercial setups. They deliver power through a single alternating voltage. Three phase power systems, on the other hand, are used for larger electrical loads as they deliver three alternating currents that are out of phase by 120 degrees. This ensures a continuous flow of power and greater efficiency in transmitting electricity. You can see the DC again is just going straight. AC is uh, this is a sinusoidal. There are two ACs, and the first one is the sinusoidal wave, and they have a phase of 180, not a phase, but yeah, they have 360. They're completing 360 with the sine wave, a sinusoidal wave, and the second one is with cos. And both of these waveforms, the second one and the third one, has a phase difference of 90 degrees. Because in the first one, the waveform is coming at zero at 180 degrees, and the second one, the waveform is coming at zero at 90 degrees only. So the voltage, if it is for voltage, if you assume this is for voltage, if you assume this is for current, then I am assuming this is for voltage right now. So I would say in terms of, I will call it in terms of voltage. So if the voltage is zero in the second case, second case, which is the first AC, or okay. So the voltage is zero in the first AC case at 180 degrees, and the voltage is becoming zero at 90 degrees in the second case. In the first case, it is at high positive at 90 degrees. In the second case, it is high positive at 0 degrees. And these are the formulas of single phase power and three phase power. The single phase power is very simple. P equals V into I, where V is voltage, I is the electric current, and P is the power. For three phase power, we have three phases, so they will have their separate powers. And in this case, what I've done is I divided them into three different voltage and current voltages and currents, and where cos theta is the power factor. We'll come to talk about it. But if the voltage is same and the current is same for all of them, if there is no phase imbalance or current phase imbalance in all three of them, then their voltages will be same and their currents will also be same. In that case, P, or the power, the three phase power, will be equal to under root 3 VI cos theta, where cos theta again is the power factor. Okay, here we go. The power factor. Oops. Okay. In AC systems, the power factor is an important concept, what measures the efficiency of power usage. It is defined as the ratio power factor is defined as the ratio of real power, or the actual power, which does the actual work, to the apparent power, which is supplied to the circuit. So, and it, and it is shown with cos theta. A high power factor indicates efficient use of electricity, whereas a low power factor suggests wasted energy. Power factor correction is often used in AC systems to improve efficiency and reduce energy losses. So in this diagram, in this example, kVA is the apparent power, which is the total power which was supplied to the system. kW is the actual power, the power which is used for some, or the power which has done some useful work. kVAR is the reactive power which is the wasted power, uh, which could not be used, yeah. So how can we correct them, and why this wastage of power or this reactive power comes into play? So whenever we have an inductive circuit, our voltage leads the current, or in terms of current, the current lags the voltage. Whenever there is a inductive circuit, there is an inductive load in that circuit. And if there is a capacitive load, the current leads the circuits. That's why the phase difference, or that's why this phase difference in the current and the voltage. This difference is the power factor. How we can correct this? So if we talk about inductive circuit where there is an inductive load and the current is lagging, so we can introduce a capacitive or capacitor bank or a capacitor in that circuit, because with capacitor the current will lead. So the lagging current will start to lead now, and with it being leading, it means the voltage and current will now be in complete phase, or completely in phase with each other, in sync with each other. In a capacitive circuit, we can, in the capacitive circuit, the current is leading. Therefore, to make it lag, a bit so that it can come in phase with voltage, we have to use an inductive load there or an inductor there. Now, there are some there are some definitions that um, I would like to talk about for solar, so which I am calling a solar dictionary here. So the radiation, the first thing about the radiations. So radiation is the energy emitted from a source. When solar radiation falls on a surface, the amount of power it generates per unit area is known as the irradiance. I'm repeating it again. When solar radiation, so first of all, radiation is the energy emitted by the source, which is the sun here. The total energy emitted by the sun is called the radiations. Um, when those solar radiations fall on the surface, the total amount of power that it generates per unit area is known as the irradiance, and the irradiance per second is called the irradiation. So, for example, I'm just giving an example of irradiance here. If irradiation falls on 1 meter square surface, the power that it generates, if the radiation falls on a 1 meter square surface, the power it generates is called the irradiance or unit irradiance. What are peaks and hours? So the peaks and hours refers to the period during a day when the solar irradiance exceeds 1000 watt per meter square. 1000 watt per meter square is again the irradiance. Okay, so the peaks and hours refers to the period during the day when the sun irradiance exceeds 1000 watt per meter square. Typically, this happens when the sun is at its highest point and its intensity is the greatest. During these hours, solar energy system operates at maximum efficiency. And with this diagram, I can zoom in here. With this diagram, you can see the peaks and hours are in between 8:30 to 3:30 here. Okay, so that's it for today's class. Thank you very much for joining in.